Okay, students, I'm just going to do a quick debrief for the structure elucidation exercise 1, question 1. Okay, so first, you probably remember that in most cases, I advise you guys to draw out a reaction scheme, but you might realize that actually question 1 is simple enough to give that a miss. And another thing regarding how do you write your information and deduction would be the information is essentially just stuff you can get from the passage. So I just use the first one as an illustration. So for example, it was mentioned that C gives silver mirror with Tholen's reagents, right? So with this in mind, you can easily conclude that C contains aldehyde group, and it underwent condensation reaction with Tholen's reagents. Okay, so some of the things that you might want to take note of for deduction would be you can think about the possible structural features, and you can also think about what's the type of reaction that C undergoes. Okay, then moving on, the second piece of information, it's not very useful for us here if you realize. The reason is because you don't know the relative molecular mass of C. Okay, but what you can possibly say would be well, I mean, C undergoes some form of reduction and then etc., which I don't think we want to write them down at this stage. And then for the third piece of information, I think it's really important because it tells you that C underwent strong oxidation, okay, to give F, G, and H. Okay, so you get 3 compounds here. Okay, so let me just adjust this a little bit so that you wouldn't get so confusing. Okay, so give you 3 compounds. So you can say that oxidative cleavage of CC double bond occurs as a deduction. Okay, then if you want, you can even conclude that there are 2 CC double bonds. So but don't commit, so just say 2 CC double bond may be present. Okay, I think that works. Okay, then I think from here on we can easily get the structure for C. But before that, maybe I'll move on to the ChemDraw so that you can see what exactly is going on. So okay, so in this case, for C here, okay, we know that it underwent a reduction. Okay, and then the product, maybe it will be good for you to draw the skeletal structure out. Okay, so it probably looks like this. You have to be a bit careful about the CH and the CH3 here because a lot of the students tend to make mistakes here. So just take note of it, and then I think the rest will be pretty straightforward for most of the students. Okay, and then yep, this will be the product that we are looking at. If you want, you can number your carbon, as I often mention as one of the techniques you can look into, because it's really going to be extremely useful here. Okay, so I'm just going to change the font size and the color so that it doesn't overlap. Okay, so this is 1, and then we have 2, and then 3. Okay, I'm just going to write out all the numbers nicely. Okay, so you can have 2, and then 3, and then 4, 5, 6, 7, 8, 9, and then 10. Okay, then after that, you also realize that C underwent oxidative cleavage. So in this case, it's a strong oxidation. Okay, and then it gives you F, G, and H. Okay, although you are not exactly given what F, G, and H are, but you can easily tell from the molecular formula, because for F it has 4 oxygen and 2 carbon, then and only 2 H's. So it can only take one identity, which is actually ethane dioic acid. Okay, because it has no other choice if you scrutinize it properly. Yeah, so this is probably the only product that you can think of. Some of you might be wondering why wouldn't it give you CO2, but well, I mean, sometimes the question works this way. If I give you CO2, then you probably cannot predict what the final product is. Yeah, and whether to get CO2 or not, it really depends on the temperature as well. So you can take it that you have to work based on the information given to you. Okay, for G, having 3 carbon and oxygen, you can only predict a ketone. Some of you might be wondering why not an aldehyde. You probably want to know that strong oxidation condition, aldehyde might not be that possible. Okay, and even if it's formed, it will straightaway give you carboxylic acid. So ketone will be the best way out. Okay, alright. So right now, if you look at the whole thing, right, we are just left with one more, which is HC5H8O3. Which some of you might be a bit concerned. How are you going to get H out? Okay, but before you move on, right, let me just enlarge this. ChemDraw, right? You notice that the only part where I can fit a potential structure of C in, right, okay, at this corner where carbon 1, 2, and 3 is, right, is actually this ketone. Okay, so straight away I should be able to number them pretty comfortably like this. Okay, yep. Then if you look at this particular ethane dioic acid, right, throughout this whole structure, I think the only place where you can potentially decide where these 2 carbon are, right, will be right at the end. Yeah, because if not, you realize you're gonna end up with too many CC double bonds. Okay, so with that, then let me just put this as 8 and then as a 9 in here. Okay, then I think the remaining will fall in quite nicely, because you would expect, based on this, that a hypothetical structure of C. Okay, so let me just shift it down. Shift it here. A hypothetical structure of C, right, will probably contain a double bond between 2 and 4. Because oxidative cleavage between 2 and 4 will give you propanol, right? And then a hypothetical structure of C, right, you would probably expect carbon 8 to have a CC double bond as well. So if I put in a CC double bond between carbon 8 and 7, and then of course C for C9 is not an alcohol, it's actually a ketone. Yeah, so in that case, this will sort of give me a hypothetical structure of C. Then if you try to think about it, does it work? Well, I mean, if I cleave here and I cleave here, it does work, right? Because if I cleave those 2 parts, then the remaining part of the molecule, I'm going to use an eraser to just erase this part. Okay, so the remaining part of the molecule will look like this and like this. Okay, of course, with the carboxylic acid and the ketones and the ketone in. Okay, sorry. Okay, and then the carboxylic acid over here. Yep. Okay. Yep. Then okay. So if you scrutinize this 5-carbon structure, I think you can easily tell that the formula is C5H3456788O3. Okay, which kind of like fit into this C5H8O3. Okay, so with that, I will be able to conclude that my structure of G is as follows. So this is my G, and then I think from here you can kind of conclude that the structure of C will be like this. So this will be the structure of C. Okay, and then the final piece of information that we haven't sort of answer is actually why this piece of information. Okay, is actually to act as a confirmation that the CC, or rather the pi system, okay, present in C has a total of 3. Okay, how do we know that? There are 3 pi systems. The relative molecular mass of C is 152. So if you take 0.1 divided by 152, I think you should get about 0.0065 something. Okay, then if you calculate the number of moles of hydrogen here, you take the ratio, it's very nicely fall into the category where 1 mole of C reacts with 3 moles of hydrogens. Okay, so that means that the formula that you come up for C is on the correct track. Okay, students, we're going to move on to question 2. You notice that there's a large number of carbon, but I think from the products in the 4th paragraph, you realize that it's quite easy to actually piece them together. Okay, so first, we have to be clear of the number of carbon. At the start, we have 20 here, and then upon reduction, on the first clue that we are given, the 20 carbon remains. Okay, but I think the crucial thing here would be actually the number of H's. Okay, it increases from 32 to actually 34. Okay, so and you know the role of lithium aluminum hydride in dry ether. It either reduces ketones, aldehydes, or carboxylic acids. Okay, and you also notice that the number of oxygen reduces from 2 to 1. I think these are enough clues to tell you what you might have at the start. Okay, it's likely to be a carboxylic acid. Okay, so I think here you can make a conclusion that A is reduced by lithium aluminum hydride dry ether. Okay, to B. And then there are several things you can actually conclude here. A is a carboxylic acid, and B contains a primary alcohol. Okay, I think these are some of the clues that that will help you problem solve. And those of you who are maybe a little bit like me, die-hard fan of degree of unsaturation, you can do the calculation if you want. So you can easily tell us that the degree of unsaturation of U of A is, you can do a quick calculation, 22, so that would be 42, right? So 42 minus 32, it's 10 divided by 2 is 5, of A is 5, and degree of unsaturation of B is, I think you can easily do the calculation, it tells you that it's 4. Okay, so if you wish, you can make the conclusion that both A and B contains 4 CC-1. Okay, but of course this is really a little bit on hindsight, but and you can only make this kind of conclusion solely because you are aware that A contains a carboxylic acid, and therefore the rest of the non-polar hydrocarbon chain, the only degree of saturation must come from CC double bonds. Okay. Of course, you can argue that this might be far-fetched as well, because it could be triple bond. Yeah, I mean, yeah, that's why maybe it might be good to add the word may contain 4CC double bond. Okay, but later on you will see. Okay, and then after that, they mentioned that when A is heated with ethanol and corn sulfuric acid, it gives you C. And then after that, after the reduction, it gives you D. So I think from here, you can further make the conclusion. Heated under reflux. A is heated under reflux with corn H2SO4 to give C, and then after that C reacts with H2 to give D. Okay, I think here there are several conclusions you can make. First, I think you can tell that C is an ester, right? Okay, and for the case of D, you can say the ester group remains in D. Okay, but the rest of remains in D, and the rest of the CC double bonds gets reduced by H2. Okay, you can make this conclusion, not a problem. Okay, and our most important clue actually comes from this oxidative cleavage. Okay, because it's only with this that you can actually piece up and get your final answer. Okay, so from here, C reacts with corn H2 and so forth. So you can see reacts with KMNO4 to give and then blah blah, and then you can just copy everything in to give 3 products. Okay, products in a 1:1:3 ratio. Okay, I mean you can shorten it, and then I think the conclusion here would easily be oxidative cleavage occurs. Okay, and altogether you get 5 products. So I think this further confirms the presence of 4CC double. 5 products obtained, and this further concludes the initial presence of 4CC double bond in A. Okay, I think this really works very nicely, and then now we are going to go to ChemDraw, and then we're going to try to work out what C is. Okay, so we're going to do the same thing. Let's try to work out what C is. So C undergoes oxidative cleavage. Okay, strong oxidation. I'm not going to draw the reaction scheme again because it's not necessary in this case. Okay, so we're going to go back to this. So the first compound is actually hexadioic acid. Okay, so it's hexadioic acid. Okay, so I think we're going to draw this in pretty nicely. Okay, that's it. And then the next compound is the ester part. So you have carboxylic acid right at the end, and then you have 3 CH2s. Okay, so again, let's try this. Carboxylic acid right at the end, and then you have 3 CH2s, and then so okay, carboxylic acid right at the end, 3 CH2s, and then you have an ester. Okay. Okay, so I think it fits pretty nicely. Then after that, you realize that you have E, C3H4O4. Okay, so this gets a bit interesting. So I'm just going to put it here. So we have E with the formula C3H4O4. Okay. Now, might be good to write in the formula for C as well. Which is C22H36O2. Okay, so C22 H36O2. Right. Okay, let us probably do a carbon count because I think this will kind of like work quite wonderfully. So I pasted what I did just now. So I'm just going to put in all the numbers pretty nicely. Not exactly nicely, but yeah, 4, 5, 6. Okay, and then you realize here it's actually the other end. How do I know it's the other end? Because 22 must be a long chain. Must be a long chain, maybe something like this. A long chain, a long chain, a long chain, a long chain. And then after that, you are kind of like cleaving it somewhere like this, like this, like this, and like this. And then therefore you get fragment 1, 2, 3, 4, and 5, etc. So with just a little bit of guessing, right? I mean hypothesis in that sense, you realize that this fragment and this fragment must be found at both ends, which kind of makes sense because the ester must be on one end because the ester part is not touched. And then this alkyl chain, if it's touched, the other end will be the carboxylic acid. Okay, so I can safely say that this is right at the other end. So therefore, when I number them, I will give them a very big number, 22, right? Because the maximum number of carbon is 22. Okay, so this is 22. So let me just put them in, and then from here is 21, 20, 19, 18, 17, and then 16. And then if you realize, right, everything really falls on very nicely because the remaining number of carbon that you want to play with kind of fit because you're left with 3 of this. Am I right to say that? Okay, so let us just go back to this. Going to see. Yes, I hope I didn't make a mistake in the 1:3 ratio. Yep. Yep. Okay. So I didn't make. I hope I didn't make a mistake. So in this case, I'm left with 7, 8, 9, 10, and then 11, 12, 13, 14, 15. Okay. So let me just. Yeah. Sorry for being a bit slow. 13, 14, 15. Okay. So you realize that these 3 belong to one carbon. Sorry, one molecule. These 3 belong to the other one, and these 3 belong to the other one. And they must be the same thing, and they are therefore E. And the only way for me to connect these 3 molecules to these 2 final fragments is that the E must contain a carboxylic acid. Or rather, 2 carboxylic acid. Okay? So with that, then, and there are 3 fragments of E. So that kind of like make life really easy because all we need to do is just draw the molecule. Draw E out, and then put in the oxygen. Oops. Okay. And then after that, put in the numbers, right? Okay, I'm just going to copy, then everything else will be very nice. Okay. stop being OCD for a little while, and then I just want to make sure that, oops, just want to make sure that everything else fits. Okay. Yep. Okay. Yep. I think that works. So therefore, I can kind of conclude that for C, right, the original CC11 must be between C6 and C7, C9 and C10, C12 and C13, C15 and C16. Okay, so I hope you get it. And then, therefore, from here, I will be able to connect them up using a very long chain like this. Okay, and then I will now try to put in all. So it's 2, 4, 6. So this is the original one. 7, 8, 9, 10, 11, 12, 13, 14, 15, and then so this is 16, and then 17, 18, 19, 20, 21, 22. Okay, this 21, this 20. Okay. So I hope from here you can see how everything falls in nicely. Okay, I will just try to copy the numbers in. Okay, in case you already get what I'm trying to say. Okay, 6. Okay, I think now it works wonderfully. Okay, then it's 7. Okay, so this is 9, and then after that, and then 10 and 12. Okay, and then after that, 13, 14, 15. And then for 16 onwards, I think the rest will fit in really nicely. Okay, hopefully. Yeah, almost. Not perfect. Okay, so in that case, this will be your C. Okay, so if you know what C is, I think you can easily tell me what is A.